Okay friends, so today we're going to talk about rotational dynamics, that is movement of a spherical or a cylindrical body along a surface. So let us consider that there is a surface, and on this surface a spherical body. It can be a sphere, it can be a cylinder, it can be a ring, it can be a disc. It is moving. In this case we have got two situations. Number one is rolling without slipping. It is also known as pure rolling. And in second case we have rolling with slipping. Slipping is same as skidding. Now what do you mean by skidding? Suppose you are driving a car and you see someone in front of you and you suddenly apply brakes. Your wheels will get locked, that is the rotational motion will stop. However, the car will still move a certain distance before coming to standstill. That is, the translational motion still continues. So this is known as skidding. So we are considering two cases. Number one, there is pure rolling. There is no skidding. The body continuously rotates. And number two, there is rolling as well as slipping happening simultaneously. So first of all, it is necessary to understand what are the important conditions for a body to have a pure rolling motion, that is rolling without slipping. Let us consider a situation in which we have a sphere and it is moving on this surface. Let's take this as point A. Let O be the center of mass. Suppose the body completes one full revolution in certain time t and it comes over here. So this point is now A dash and this center of mass is say O dash. So how much distance is covered from A to A dash in one rotation? The distance covered is 2 pi r, obviously, which is the circumference of the circle. And say it takes time t, and let the velocity of center of mass be v. Then you know speed is distance upon time, so the linear distance upon time is v. Now let us consider the angular aspect. In one complete rotation, the angle covered is 2 pi. Obviously in the same time t. So what is the angular velocity omega? It is the angular displacement upon time. Now look at these two equations. This 2 pi upon t is equal to omega. If I substitute here, then what do I get? Is v is equal to omega into r. It means when the velocity of center of mass is r omega, the body will have a pure rolling motion. So this is a very important aspect that you must understand before we proceed, that when the velocity of center of mass is r omega, where omega is a rotational velocity, angular velocity. So when angular velocity and center of mass are related by the relationship v, velocity of center of mass is equal to r omega, then the body will have a pure rolling motion. Obviously, if velocity of center of mass is either greater or less than r omega, we will have slipping as well as rolling. So for pure rolling, the velocity of center of mass must be equal to r omega. So if velocity of center of mass is less than r omega, or if the velocity of center of mass is greater than r omega, we will have rolling as well as slipping, both simultaneously. Okay. Now, a body as it starts moving on a rough surface will always try to attain a condition of pure rolling, because in case of pure rolling there is minimum restriction or minimum opposition. Let us try to understand this. Suppose the body wants to attain a case of pure rolling, and we have case 1 where velocity of center of mass is greater than r omega. Then the body will behave in such a way, it will try to reduce the velocity of center of mass, and at the same time it will try to increase the value of omega, so that at one stage velocity of center of mass will become equal to r omega, right? So if velocity is more than omega, this will decrease, this will increase. At one stage both of them will become same. It's very simple to understand. Suppose velocity of center of mass is 10 and the value of r omega is 5. It will so happen that this 10 will go on decreasing, 5 will go on increasing. At one particular stage they will become same. Exactly opposite will happen if velocity of center of mass is less than r omega. Again the same thing will happen. The one which is bigger will try to decrease, the one which is smaller will try to increase. At one stage both of them will become same. Now a frictional force plays a very important role in this situation. So let us try to understand the direction of frictional force in both the cases. Now in this case the force of friction attains different directions depending upon situation. So let us consider both the cases. Case 1 is when the velocity of center of mass is greater than r omega. So what is desirable? It is desirable to reduce the linear velocity, and it is desirable to increase omega. Now let us see how the force of friction will play an important role in deciding this. This is the point, and this is the velocity of center of mass. Let us assume that the sphere is rolling in this direction. It is moving forward. Now I want to decrease the velocity of center of mass, so there must be an opposition, or the force must act opposite to the direction of motion. As the body is moving to the right, if you want to decrease the velocity, of course the force of friction will act in the opposite direction. So F will act in this direction. Now please see how F will help to increase the value of omega. You can see the torque acting due to this force at this particular point is F into R, and it is in the clockwise direction. It is same as the direction of omega, and therefore this force of friction producing clockwise torque will increase omega. At the same time the force of friction which is opposite to the velocity of center of mass, which is opposite to the motion, will decrease V. So in this way VCM will go on decreasing, omega will go on increasing, and at one stage you will have VCM is equal to omega. When VCM becomes equal to omega, the force of friction will disappear. Right? Now see, let us understand how does this happen. At this particular point there is a translational velocity which is same as velocity of center of mass, and we have taken this as r omega, because VCM is equal to r omega is a condition for rolling without slipping. At the same time there is a velocity in the opposite direction which is due to rotation, and that is also r omega. So this r omega and this r omega will cancel each other, and as they cancel each other, this particular point virtually does not have any movement, so there is no force of friction. This point is also known as ICR. It is instantaneous center of rotation. It is as if the entire body rotates about this point. So please note that In case of pure rolling, the force of friction disappears provided there is no external force. It is extremely important to understand. The force of friction will become zero in case of pure rolling in absence of external force. It is extremely important to understand this, that the force of friction will become zero in case of pure rolling in absence of any external force. That is, you just leave the body on its own, then the force of friction will become zero, and when VCM and R omega becomes equal, there is no opposition now, and the body will continue to move in a pure rolling state. Okay, now let us see condition number 2. Let us see condition number 2, in which VCM is less than R omega. Let us see the next condition, in which VCM is less than R omega. Now what is desirable? It is desirable to increase the velocity of center of mass, and it is desirable to decrease the value of omega. Again, let us consider the situation. There is no external force. If you want to increase the velocity of center of mass, then the force of friction must support it. So the force of friction will act in this direction. Now please see the direction of torque acting about the center. This torque of F is acting in the anti-clockwise direction, which is opposite to omega. Omega is moving in clockwise. So the force of friction will oppose the rotational motion, and that will result in decrease in omega. Again, at one stage, V will go on increasing, omega will go on decreasing, and VCM and R omega will become equal. When this happens, the force of friction will disappear because there is no external force. I am repeating this again and again. The force of friction will disappear in case of pure rolling motion provided there is no external force. If you are pulling this continuously with some force F, then the force of friction will not disappear. It will still be there. Okay. So now we will consider some examples to illustrate the points. Let us take examples from H.C. Verma. It's a standard book on physics, rotational motion. I am referring to page number 190 of H.C. Verma. So I have H.C. Verma page 190, part 1. It is example 27, 28, 29. So many examples are there. So let us consider example 28. What they are saying is, there is a sphere of mass m and radius r. This is the sphere of mass m and radius r. It is moving on a rough horizontal surface, and its translational velocity is v0. So they have given the translational velocity, that is velocity of center of mass, is given as v0, and its rotational velocity, that is omega, is given v0 upon 2r. Right? We are supposed to find the translational velocity, that is what is the velocity of center of mass when it starts pure rolling. What will be the velocity of center of mass when the body starts pure rolling? Now let us see here. What is the desired condition for pure rolling? The desired condition for pure rolling is that omega should have been in the beginning V naught upon R. Had omega been V naught upon R, the body would have started pure rolling immediately. But omega is V naught upon 2R, that it is less than this desired value. Desired value of omega for pure rolling is V naught upon R, whereas the actual value of omega is V naught upon 2R, which is less than the desired value. And that is why the body will not have a pure rolling motion. Now in this case, the situation is that omega is less than velocity, required velocity. So omega will try to increase and V will try to decrease, as we have seen in the previous case. As omega is less than the desired value, it will try to increase and V will try to decrease. At one stage, both of them will become same. So let us try to understand how it happens. Let me redraw the figure for you. Now what will be the situation here? Let us take this as omega naught, initial velocity, V naught upon 2R. Now, see, I have already discussed this. Omega is less than desired, whereas V is more than desired. So, I want to increase omega, I want to decrease V. Both of them must happen simultaneously. I want to increase omega and I want to decrease V. So, where will the force of friction act? I want to decrease V and I want to increase the value of omega. So the force of friction will act opposite to V naught. I think this point is fairly clear. This force of friction which is acting opposite to V naught will decrease V naught. At the same time, the torque of F at the center is clockwise. Omega naught is also clockwise, so it will help to increase the value of omega naught. Now we are going to use two equations, that is Newton's equations of motion. You can see that the only force acting is the force of friction F. So this force of friction is going to produce an acceleration. So I am going to write here F is equal to ma. But please note that this is deceleration because it is opposite to the motion. So it is going to produce a deceleration. So I have to write it as minus ma. Or your acceleration is negative. Or you can say F is equal to ma and you can take negative value of acceleration. So let us say V equal to V naught minus at. That gives me V is equal to V naught minus, what is A here? A is F upon m into t. That is the first equation. What is the second equation? The second equation is torque acting. The torque acting is given by I alpha. I hope you know this. So torque acting is I into alpha. What is the torque? The torque is force of friction into R. So force of friction into R. It is a solid sphere. So the moment of inertia will be 2 by 5 mr square into alpha. And if you calculate it, that gives you the value of alpha as, I think it is 5f upon 2 mr, right? It is 5 upon 2 mr. Now we will write the equation for rotation, that is omega equal to omega naught. Please note that omega is increasing, so alpha will be positive. Omega will be omega naught plus alpha t. That is omega is equal to omega naught. What is alpha? Alpha is 5f upon 2 mr into t. Please see here what is omega naught. Omega naught is V naught upon 2r. So I can write here omega naught as v naught upon 2r. Let me write it here right now. I can write it as v naught upon 2r. This is my equation number 2. And you have to excuse me, I have to rearrange the things. Look at this term ft upon m. I am going to replace this term ft upon m from here. What is ft upon m? Ft upon m is v naught minus v, right? I hope you are following this. It is simple rearrangement of equations. It's not a big deal. Or let me write ft upon m as, see here, ft upon m will be omega minus v naught upon 2r into 2r by 5. Right? Omega minus v naught upon 2r goes on this side, ft upon m, so into 2r upon 5. This value I am going to put here. So let's see what I get. I get v equal to v naught minus omega minus v naught upon 2r into 2r upon 5. Now what is the condition for pure rolling? The condition for pure rolling is that omega must be equal to v upon r. The condition for pure rolling is omega must be equal to v upon r. So I will put omega is equal to v upon r here, and that should give me my final answer. Let me just clear this, because we are arriving at the final part of our solution. For pure rolling, we have a situation in which omega must be v upon r. So let me finalize the solution here. V equal to v naught minus v upon r minus v naught upon 2r into 2r upon 5. Okay, so v is equal to v naught minus v upon r into 2r by 5 plus v naught upon 2r into 2r by 5. This r and this r will cancel, so v plus v by 5 equal to v naught plus v naught upon 5. V plus 2v by 5 equal to v naught, 2r will cancel, so it is 5 plus 2, that is I think 7v upon 5 is equal to 5 v naught plus v naught is 6 v naught upon 5. and that gives me the final answer as V as 6 by 7 times V naught. So when the body starts pure rolling, its velocity is 6 by 7 times V naught. So this is the way we obtain this relationship. You can also find the time required to attain this. You can use the equation V equal to U plus AT and all. You can also find the time, after how much time, if they ask you after how much time it starts pure rolling, you can simply use the equations of motion and you can get the value of T. You can also get the value of frictional force in the beginning, but please note, when this happens, the force of friction disappears. Now interestingly, there is one more extremely simple approach to solve this sum. So I am also going to provide you an alternative method. It requires a little bit of understanding. Let us see the situation. I am going to use the principle of conservation of angular momentum in absence of external torque. Okay, now what are the forces acting here? There is a force of friction acting in this direction. So if I take moments about point A, there is no force acting at, there is no torque acting at A, because force of friction is acting through this point, so there is no momentum. So about point A, there is no external torque. As there is no external torque, the angular momentum is conserved about point A. So what is the angular momentum before, at the beginning, that is angular momentum at the beginning? The angular momentum at the beginning will be the angular momentum due to translational motion as well as angular momentum due to rotational motion. What is angular momentum due to translational motion? It is m into v naught into r. And what is the angular momentum due to rotational motion? It is I omega. I is 2 by 5 mr square into omega naught. When the body attains pure rolling, the angular momentum due to translational motion will be m into v into r, where v is the velocity of pure rolling, plus 2 by 5 mr square into omega, where omega is also a velocity when there is pure rolling. Okay. Now when there is pure rolling, you can write omega as v upon r. Correct? Okay. Please see the direction here. Since the sphere is moving clockwise, omega is also clockwise. This is positive. So please note that when you find angular momentum about any other point, you have to consider angular momentum due to translational motion as well as rotational motion. So let us now substitute the values. I have m into v naught into r plus 2 by 5 mr square. What is omega naught? Omega naught is v naught upon 2r. Is equal to mvr plus 2 by 5 mr square. And when there is pure rolling, I can write omega as v upon r. Now we have to cancel the things, rearrange the things, and let us see what we get here. Mm will cancel definitely, so let me write here v naught into r plus this 2 will cancel, v naught upon 5r, sorry, v naught r upon 5, and this is equal to v into r plus 2v upon 5r. Right, again rr will cancel, you will get v naught plus v naught upon 5, that is 6 v naught upon 5 is equal to V plus R is cancelled everywhere. I am cancelling R. You can see here this goes, this goes, this goes, this goes. 5 plus 2 7 V upon 5. You get the same answer. You can see V is 6 by 7 times V naught. So this is another method by which you can find a solution. Now let us go ahead with another problem from H.C. Verma. It is solved in a very different way. I am going to try a different approach here. This is problem number 29. H.C. Verma. It is page number 191. The topic is rotational mechanics. Part 1. Let us try to understand the situation. Here is a sphere on a rough surface. Its radius is r. There is a small particle of mass small m. Mass of the sphere is capital M. It hits the sphere with an initial velocity v0 at a height h. Due to the impact, obviously the sphere will start rolling. This particle, after hitting the sphere, sticks to it so that both small m and capital M move together. We are supposed to find the value of the height h in terms of r, so that the sphere immediately starts pure rolling. Goes into pure rolling. So please try to understand the problem here. There is a small mass particle, small m, whose mass is negligible compared to mass of sphere. It is moving with a velocity v0. It hits the sphere at a height h and sticks together. Due to the impact, the sphere will start moving in the forward direction. We are supposed to find the value of height h in terms of r, so that the system will immediately start pure rolling. Again, we will do the same thing. We will try to apply the principle of momentum conservation. Let us first understand the linear momentum conservation. What is the momentum of the system before impact? M into V0. The momentum of the system after impact is small m plus capital M, as both of them move together with the velocity, say V. So we have got m into V0 is small m plus capital M into V. This is one equation we have. Now let us apply the conservation of angular momentum. What is the angular momentum of the system about point A before impact? It was m into V0 into h, because the height is h. What is the angular momentum after impact? The angular momentum after impact will be due to translational motion as well as due to rotational motion. So angular momentum due to translational motion will be, now you can consider the mass of the body as m plus m, because it is together, mvr. This is due to translational motion. And what about due to rotational motion? Due to rotational motion it will be two by 5 mr square. It is I into omega. Now you know, for pure rolling you can directly write omega as v upon r. I hope you can understand this. You can just write here omega as v upon r. This is I, which is 2 by 5 mr square into omega, and for pure rolling omega must be equal to v upon r. Right? Okay. Now let me divide by m plus m on both the sides. So m v0 upon m plus m into h equal to v into r plus 2 by 5 times V into R. Now what is M upon M plus MV? MV0 upon M plus M. MV0 upon M plus M, you can see here, it's same as capital V, right? So what do you get here is VH, take V common, R plus 2R by 5. VV will cancel, and what H will get is R plus 2R by 5, that is 7R by 5. So the height should be 7R by 5 for the body to start pure rolling, and this is the same answer which is given in H.C. Verma, but they have done it in a different way. My way of doing the sum is different. I have taken the conservation of momentum about point A. I get the answer very quickly. So this is another example from H.C. Verma. Now let us do one unsolved sum from H.C. Verma, which depicts this funda. Let me search. It is on the last page of the chapter, page number 200, sum number 85. Question number 85, again from the chapter of rotational mechanics. You can refer the textbook. I am doing sum number 85. This is a solid sphere set into motion on a rough horizontal surface with a speed v in the forward direction and the angular speed v upon r in the anti-clockwise direction. So the situation is a little different here. It is moving with a speed v in the clockwise direction because it is moving forward. Had the speed, rotational speed, have been v upon r in the clockwise direction, the body would have started pure rolling, but that is not given. What is given is the initial speed is v upon r is in the anti-clockwise direction and not in the clockwise direction. So the initial speed omega naught is given v upon r in the anti-clockwise direction. Please note, had it been clockwise, the body would have started pure rolling immediately, but here the omega naught is in the opposite direction. We are supposed to find two things. We are supposed to find the linear speed of sphere when it stops rotating. They are asking us what will the linear speed when the body stops rotating. And secondly, they are asking what will the linear speed when it starts pure rolling. Now it is extremely important to understand what is going to happen here. Here omega is v upon r. Unless and until the direction of omega gets reversed, pure rolling is not possible. So when the direction of omega gets reversed, at one stage the body will stop, obviously. At one stage the body will stop and then it will start pure rolling. So in the first situation, the value of omega is going to become 0 and then it is going to start pure rolling. Now let us see the situation. I want the value of omega to become 0 because it has to be reversed. So the applied torque must oppose, the force of friction must oppose the value of omega naught. So in this case, omega naught is in the anti-clockwise direction. The force of friction must act like this so that it will produce a torque in the clockwise direction about the center, and this will reduce the speed of the body. Again, let us apply the principle of conservation of angular momentum about point A. Please note that conservation of angular momentum is a vector equation, and proper sense of direction is extremely important. F, as it acts along A, doesn't have a moment arm, so there is no external torque acting at point A. So let us see what is the angular momentum before or just in the beginning. Angular momentum in the beginning. So the angular momentum in the beginning is again due to two sets, due to number 1 rotational motion and number 2 due to translational motion. So the angular momentum due to translational motion, as we see, is mvr, and angular momentum due to rotational motion is I omega naught. Now I have made a mistake here deliberately. I have written this positive sign, which is incorrect, because we are taking clockwise direction as positive, right side as positive. Since it is opposing, I must write a negative sign here because it is in the opposite direction. So I must write this as minus and not plus. So the momentum in the beginning is mvr minus I omega naught. What is the momentum afterwards? That is when it stops rotating. When it stops rotating, let the velocity be v dash. So I will have m into v dash into r. As it stops rotating, omega is going to be 0. So obviously this term will not come. And let the velocity be v dash when this happens. So let us now substitute. I will get mvr I is 2 by 5 mr square. Omega naught is given as v upon r. Please note, it is there in the problem. Is equal to m into v dash into r. Cancel m and r throughout. If you cancel m and r throughout, what remains here is v. You cancel m and r throughout, what remains here is 2 by 5v is equal to v dash, and that gives me v dash as v minus 2 by 5v, that is 3 by 5. So when the body stops rotating, the linear speed is 3v upon 5. This is done by using conservation of angular momentum. Now let us consider the situation, second thing, when the body starts pure rolling. Okay, can I remove this? When the body starts pure rolling, the only difference will be this omega will be written as v dash upon r. This omega will be v dash upon r. That is the only difference that we are going to make. So let us rewrite it quickly. So I have mvr minus 2 by 5 mr square. Omega naught is again v upon r equal to m into v dash into r. I is 2 by 5 mr square, and the new value of omega, say omega dash, it will be v dash upon r. So again let us cancel m and r. What remains here is v minus 2 by 5v. What remains here is v dash plus, I think, right, 2 by 5 v dash. So I have 3 by 5v equal to 7 by 5 v dash, and that gives me the desired answer, v dash as 3 by 7 times v. So when the body starts pure rolling, its velocity of center of mass will be 3v by 7. Let me check the answer. Sum number 85. 3v by 5 and 3v by 7. Now, sum number 86, which is just after 85, is very similar, but it is very tricky because it makes you think a little bit, and we must understand the principle of conservation of linear momentum very carefully to be able to solve this sum. So I am going to do sum number 86 on page number 200, H.C. Verma. Again the same chapter, rotational mechanics. Please refer the textbook. There is a solid sphere rolling on a rough surface with a linear speed v. It collides elastically with a wall. So this is a wall. A solid sphere moving in this direction, it collides with the wall, and after it collides with the wall elastically, means the coefficient of restitution is 1, so if v is the velocity with which it is hitting, it will come back with the same velocity. Find the speed of the sphere after it starts pure rolling in the backward direction. So we are asked to find the value of speed of the sphere at pure rolling condition. Okay. They are saying that a solid sphere is rolling, so in the beginning it is having a pure rolling motion. So this particular motion is of pure rolling. But what will happen after collision? Let us try to understand this. In the beginning, the sphere is rolling purely. It is given in the problem. I am not assuming it. The sphere which is having a purely rolling motion without skidding is going to make an elastic impact here, and after making an elastic impact it will reverse its direction. After it reverses its direction, it does not remain pure rolling. I will explain why. They are asking us what is the velocity of center of mass after it resumes pure rolling. Now let us try to understand this principle very very carefully. This is a wall and a sphere is hitting the wall. At this particular point there are two velocities. One is a linear velocity which is v, and one is the angular velocity. You can see that the sphere is rolling in this direction. So the angular velocity at this point omega will be v upon r because it is pure rolling. So omega will be v upon r. This is known as the line of impact. An extremely important principle of collision is that the velocity changes occur only along line of impact. You will learn this in engineering also. That is, there is no change in velocity. There is no change along a line which is perpendicular to line of impact. That is, you can see that v upon r is perpendicular to line of impact. So v upon r or omega will continue to be in this direction. As it is moving like this, v upon r will continue to be in this direction. However, the velocity v will reverse. So after the impact, this velocity v will become velocity to the right, but omega, that is v upon r, will continue to be in the anti-clockwise direction. You can see this situation is exactly same as in problem number 85. So let me redraw the situation, what happens after impact. Okay, what is happening after impact is the linear velocity along the line of impact will change, and since it is elastic, v to the left will become v to the right, no issues about it. However, omega, which is v upon r, will continue in this direction, isn't it? Now it is exactly the same situation. Had omega been in the clockwise direction, the body would have started pure rolling, but here omega is in the anti-clockwise direction, whereas v is moving in the forward direction. So again, if you want a situation of pure rolling, then omega must be in the clockwise direction. So same thing will happen. First omega will reverse its value, it will become 0 first, and then it will attain pure rolling. So when it attains pure rolling, you remember in the previous example we had the value of v dash as I think 3 upon 7v, and here also we will get the same answer. When the body resumes pure rolling, its velocity will be 3v upon 7. You can check the answer of sum number 86. I hope you have understood this concept very carefully. Please note that the change in the velocity occurs only along line of impact. Perpendicular to line of impact, there is no change in the velocity. So this v upon r, which makes omega in the anti-clockwise direction, even after impact it will continue to be in the anti-clockwise direction. So this sum becomes exactly same as sum number 85 after this particular concept has been explained. Let us do one last example on this rolling. Let us take a solved example here. I am doing sum number 27. I think it has been solved, but still let us do it because there is an external force acting in this case. So I am doing example number 27. H.C. Verma. Page is 190. Okay. See the situation. There is a force capital F which is acting tangentially at the highest point of a sphere. This is a rough surface. It is given that the sphere is having pure rolling. It is given in the problem that the sphere is pure rolling. We are supposed to find the acceleration of the sphere, acceleration of center of mass, obviously in terms of F and M. In terms of F and mass of the sphere M. Okay. Now the first important question arises regarding direction of force of friction. Let us consider two situations here. Suppose the force of friction acts in this direction. If the force of friction acts in this direction, it will support the original force. This will make the velocity v. It will go on increasing. At the same time, this force of friction will produce a torque at the center in the anti-clockwise direction, that is opposite to omega. And this F will produce the force of friction here in the clockwise direction. So one will support, one will oppose, right? So this may increase in the value of omega, this may result in decrease in the value of omega. That is one case. Let us consider the second case, in which the force of friction F is in this direction. Now this force of friction, since it is acting opposite to F, will produce a net decrease in the value of V, or may it produce increase, but what will happen to omega, you can see here. This F will produce a clockwise torque. This F will also produce a clockwise torque. So the value of omega will continuously go on increasing. The value of omega will continuously go on increasing. However, the value of V, look at value of V. This F and this F are opposite. So this frictional force will oppose the applied force, and that may decrease the value of V. And therefore, this particular situation is not possible. This is the possible situation. Or you can do one thing. You can get the situation like this, solve the sums, you will automatically get absolute or a negative answer, and that will make you understand that the force of friction is acting to the right. So to find the direction of force of friction, you first must understand this, that in this situation F and F are both supporting, and that will continuously make omega increasing. Omega will go on increasing. At the same time, the value of V, which is being opposed by this, may go on decreasing, and that is why this situation is not possible. Now we can apply D'Alembert's principle, and we can get the value of acceleration. What does the D'Alembert's principle say? Sum of all the forces is equal to mass into acceleration. Sum of all the forces acting is mass into acceleration. So capital F plus small f is equal to ma. Okay, so this is the D'Alembert's principle for translational motion. Now let us look at rotational motion. What is the torque acting? The torque acting is F into R in the clockwise direction, which is positive, and small f into R is in the anti-clockwise direction, so that will be negative. This torque is going to produce an acceleration I alpha. I is into alpha. So this is second equation. As we know, when there is a pure rolling, we have V is equal to R omega, and if you take the derivative, dV by dt will be R into d omega by dt. dV by dt is linear acceleration, and d omega by dt is the angular acceleration. So A is equal to R alpha. Please note, this equation is applicable only for pure rolling. So instead of alpha, I can put A upon R. And let me do that. So what do I get? Let me take R common here. Capital F minus small f is equal to 2 by 5 mr square into A upon R. You can see this R and this R will cancel, and you will get capital F minus small f as 2 by 5 ma. So this is the first equation, and this is the second equation. Just add them. Capital F and small f will cancel, and you will get 2f is equal to ma plus 2 by 5. That is 1 plus 2 by 5 is 7 by 5. Rearrange the terms, and you will get acceleration as 10f upon 7 . Now let us consider, I think, one more concept I need you to understand, and that is rolling down an inclined plane. Sphere rolling down an inclined plane is a very commonly asked problem. Let us try to understand that. It can be any body, spherical body, not necessarily a sphere. It can be a ring, it can be a disc. So let us understand that the sphere is rolling down, and let us talk about pure rolling again. If you remember, previously I told you, in case of pure rolling there is no force of friction, but I hope you also remember that I had put a condition that in case of rolling there will be no force of friction provided there is no external force. In this case, the force of gravity continuously acts on this sphere, as it travels down, and therefore the force of friction will not disappear even though the body is having a pure rolling motion. Please note that the force of friction will disappear in case of pure rolling only when there is no external force. So let us see, the weight mg is acting in the downward direction. This angle is theta. You can see the geometry, and this angle also will be theta. I hope you understand this. We are moving this line by 90 degree, making it vertical. This line is also moving by 90 degree, making it vertical. So the angle between the lines remains same. There are two components here. One is mg cos theta, which is acting perpendicularly downwards, and this component is mg sin theta. Now the question arises as to the direction of force of friction. Please note that mg sin theta will continuously increase the velocity as it rolls down. As it rolls down, the velocity of the center of mass will go on increasing in order that v equal to r omega holds. If v goes on increasing, omega also must go on increasing to match it. In order to increase omega, I must supply a torque which is in the clockwise direction, and that is possible only when the force of friction acts like this. This will produce a clock. This mg sin theta cannot produce a torque about center of mass because it is acting at center of mass, but a force of friction acting in this direction will produce a clockwise torque at the center. It will help increase the value of omega. So the force of friction is going to act in this direction. So this is the condition when the body is rolling down. Now the basic principles of friction and all you already know, that force is mu into r. Here the normal reaction n acting in the upward direction balances mg cos theta. So you have n is equal to mg cos theta. The force of friction is mu into n. So the force of friction will be mu into mg into cos theta. All these things you can easily understand. Let us apply D'Alembert's principle to find the acceleration of this particular body. The downward force is mg sin theta. The upward force is mu mg cos theta. The net force will be ma. So we have mg sin theta minus mu mg cos theta, or you can simply say f. We will put mu mg cos theta afterwards. Mg sin theta minus force of friction is equal to ma. This is one equation. What about the rotational funda? The torque produces F into R. So the force of friction into R is equal to I alpha. Let me take I as mk square, where k is the radius of gyration and you know alpha, I can put A upon R for purely rotational body. So F into R is mk square into A upon R. So what will be F? F will be mk square into A upon R square. Just substitute it over here and I will get the answer for acceleration. So F is mk square A upon R square. Sorry. First I have mg sin theta. So mg sin theta minus this F is mk square A upon R square. Let me cancel m throughout. I'll get g sin theta equal to k square upon R square into A plus A. If I rearrange, I will get A as g sin theta upon 1 plus k square upon R square, where k is the radius of gyration. So this is the acceleration of the sphere in the downward direction. From that you can find the value of velocity, you can find the frictional force and other values, time required to reach the ground. You can use Newton's equations of motion, you can use v equal to u plus at, and you can still get answer. Please note, you can also use the conservation of energy between point 1 and point 2. A very important aspect is that the force of friction does not do any work when there is pure rolling, because as we have seen, when there is pure rolling, this particular point has one velocity r omega in the forward direction, one r omega is in the backward direction. So as if the point is not moving virtually, and therefore there is no displacement of this point. So friction work is zero. Friction does no work in case of pure rolling. This is another important concept that you must understand if you want to apply the principle of work and energy. When there is pure rolling, work done by friction is zero, right? And the lecture has been really extended, it is more than 1 hour, but one last thing regarding instantaneous center of rotation I want to explain. Let us see the velocities at different points on a sphere or on any rolling body which is having pure rolling. So we have a pure rolling situation. Let the center of mass have velocity v, and obviously it must be equal to r omega. So please note that every point on this sphere will have same translational velocity, which is r omega. Translational velocity of every point on the sphere is same and is equal to r omega, is equal to v, that is r omega. Yes. Rotational velocity or omega, rotational velocity is along the tangent. So there are two velocities. Translational velocity is always to the right, whereas a velocity due to rotation, that is to circular motion, is along the tangent. All of you know that. So let us consider various points, say point A, point B, point C and point D. Let us assume that the rotation of the sphere is along clockwise direction. Okay, so let us pick up point C. As you know, the linear velocity is always r omega. It is linear velocity plus the velocity due to rotation is r omega along the tangent, so that is also r omega. So the net velocity will be r omega plus r omega. So the velocity at C will be 2r omega. Let us consider point B here. Again, the velocity, linear velocity, will be r omega, whereas the velocity due to rotation r omega is in this direction. So you can see there are right angles. So the net velocity will be obtained by the law of parallelogram, and velocity at point B will be root 2 times r omega in this direction. Look at point A. Again, the translational velocity r omega is always to the right, but as the sphere is rotating clockwise, the velocity due to rotation will be in the opposite direction, and therefore at point A the total velocity will be 0, and that is why we say that the point A is virtually not moving, and that is why it is called as instantaneous center of rotation. Okay, what happens at point D is the linear velocity is again r omega, whereas the velocity due to circular motion, rotational motion, you can see is in the upward direction. So the net velocity will be again root 2 r omega. In this direction. So these are different velocities at different points. But let us consider intricate points. Suppose you want to find the velocity at a point somewhere in between, then what is to be done? So we will see. We want to find the velocity at this particular point. Let's take an example, the last example. Please bear with me, and we will stop the lecture. Let us see, we want to find a velocity at a point which makes an angle 45 degree with this point. Okay, so it will have a translational velocity r omega, whereas the rotational velocity will be along the tangent. This angle is 90 degree. Okay, so what will be this angle? We want to find this angle. You can see that these are interior angles, and their sum should be 180. So if this is 45, this is 90, this also is 45. Now simply use the law of parallelogram and you will get the required answer. So the net velocity will be r omega square plus r omega square plus 2 times r omega into cos 45. So that will be 2 times r square omega square plus 2 times r square omega square into cos 45 is 1 by root 2. So it is r omega 2 plus root 2. So this will be the velocity, net velocity at a point making an angle 45 degree. Now if you use the concept of instantaneous center of rotation, then you do not have to consider the linear velocity, you have to consider only the rotational velocity. So let me explain this. We can try to find out the same answer using the concept of instantaneous center of rotation. Why I am doing it is because it is quite required in mechanics. When you will go for engineering, this will be required. So let us see the concept of instantaneous center of rotation and see what answer we get. We want to find out the velocity at this point using the concept of instantaneous center of rotation. Now, as you know, we have seen previously, this is the instantaneous center of rotation. So let me join this. Now my radius is going to be this. Let this be point B. Let me elaborate this figure here because it is very clumsy, looking very clumsy here. This is A, this is B, this angle is 45. According to the concept of instantaneous center of rotation, the body is rotating about this point, so the net velocity will be, and linear velocity will be at right angles along the tangent. So this is going to be the direction of net velocity. You know, this is R, this is also R. If this angle is 45, this angle is 90, right? These two triangles, now we have to find out the value of AB in terms of R. So how we will find AB in terms of R is a question. This angle is 90. So this angle is 45. This angle will be 90 plus 45. This angle will be 135. These two angles have to be same because this triangle is an isosceles triangle. So suppose this angle is theta, this angle is also theta, then 2 theta plus 90 plus 45 will have to be equal to 180, and that gives me 2 theta as what? 45, and that gives me theta as 22.5. Okay. Now we want to find the length AB. How will you find length AB? You can use cosine rule. I think that is the best way to find the length AB. There is no need to find this angle as such. Let us try to use the cosine rule here. Let me redraw this triangle here. Let me take this as O, and let me redraw this triangle for you. I am interested in finding the value of AB. This is point O. This angle is 135. This is R. This is R. So what is cos 135? Suppose this is X. According to the cosine rule, cos 135 will be b square plus c square minus a square, that is r square plus r square minus x square upon 2 times r into r, that is 2r square. Cos 135 is cos 180 minus 45, and cos 180 minus 45 will be minus cos theta, so this will be minus 1 by root 2. So what do we have here is, let me erase this portion. R square upon root 2 with a minus sign, of course, is equal to 2r square minus x square. So x square is 2r square plus root 2r square, or x is r into square root of 2 plus root 2. So that is x. And what is our velocity? Our velocity is x into omega. So the linear speed and total speed at the point B, total speed at point B will be given by x into omega, and that is r into omega into under root of 2 plus root 2. You can see we got the same answer as we got it in the previous thing. This is the concept of instantaneous center of rotation. It is complicated, so there is no point in doing it here, but it is necessary for your engineering studies, and that is why I have introduced it here. This is the concept of ICR, where you consider only rotational motion and the radius is between the ICR and the desired point. You find this multiplied by omega and you get a net velocity. Here you do not have to consider the translational velocity. Okay, it is more than almost it is 1.5 hours, so we'll stop our concepts of rotational mechanics. I hope I have made it fairly clear for you. If you have any queries, you can please contact me at my email ID. I think you already have my email ID, or if you don't have, you can send me a mail, or you can send a message on YouTube. Ashutosh.karmakar at gmail.com. You can please note the double A. You can send me your queries at this email. I will try to solve your sums, solve your questions as much as possible. Thank you so much.